Hello. Okay, so welcome back, and Jayadev Athreya will continue his lectures on SL2R action on spaces of differentials.
Great. So I want to resume where we left off yesterday with Mazur's criterion, which is one of the first and very beautiful connections between the orbit of a surface under the SL2R action, or a piece of the SL2R action, and the dynamics on the surface itself. So there's a link between the dynamics on the space of surfaces and dynamics on the surface itself. And this is what we're calling renormalization. And in particular, I should maybe point out, I think this caused some confusion in discussions over lunch. The word criterion is maybe not a good word here, because it's not an if and only if condition. It is an if condition. If you're not divergent, then you're uniquely ergodic. Or in other words, if you're not uniquely ergodic, your trajectory is divergent. However, there are divergent trajectories which give you uniquely ergodic vertical foliations. And there's no, as far as we know, if and only if condition that we found yet. And there's, in fact, there have been improvements of Mazur's criterion. Rodrigo Trevino has a very nice one, which involves integrability, integrating this quantity, L of xt omega t, over t, and Matt Smith, who's a student of John Chaika's, is also has some nice results in this direction. But I want to highlight Mazur's idea because it's somehow the original idea, and it's really very beautiful. Okay, so let's try and remember what all the words on this slide mean. So we have a translation surface x omega. Associated to the translation surface is this vertical flow. And we know this vertical flow preserves Lebesgue measure. Lebesgue is a transverse invariant measure on a subinterval, but it's also just you can think of Lebesgue measure on the surface. And then the question is there any other invariant measure? Okay. And we want to understand when there isn't such another invariant measure, because that will allow us to say, for instance, if there isn't any other invariant measure, we'll say that every trajectory equidistributes in the surface. It gives us very concrete information about the long-term behavior of these vertical trajectories. So unique ergodicity is a very powerful fact. So we want to know this unique, it would be nice if we have a condition that we could check that guarantees unique ergodicity. And at least, criterion, if you look at the English definition, is just something like that. It doesn't have to be an if and only if. It's you check something and the other thing works, okay? So this is something where if you check it, you will get unique ergodicity. And the condition is simply, there should be some sequence of times so that your surface kind of has bounded geometry under this renormalization. That is, when you do this, so you stretch the horizontal, you contract the vertical. That is, you kind of speed up the vertical flow. So a long piece of vertical on your original surface is now a moderate length of vertical. And what you'd like to say is that this sequence of surfaces isn't too crazy, right? At least there's some subsequence which the surface never gets, doesn't get a very narrow neck, right? It doesn't have a short saddle connection. Or you can really think about having a short curve as well. Right? So we know that this is the way to diverge in spaces of surfaces if you have a short curve, and then, well, at least in a hyperbolic picture, you'll have this kind of long funnel, and the surface will look long and thin. Even in the torus, right? If you have a short curve, you'll go from your torus looking like a donut or a kind of a truck tire to looking like a bicycle tire or an inner tube or a hula hoop or something like this, and eventually it kind of disappears. So Mazur's criterion says, as long as this thing is bounded below along some subsequence, the length of your shortest saddle connection, you are uniquely ergodic. Otherwise, in other words, if you're not uniquely ergodic, then this length actually has to tend to 0. Okay. And again, there are examples so for the torus, of course, there's only two possibilities. Either you're periodic or you're uniquely ergodic. For higher genus surfaces, there's intermediate things that can happen. You can be dense. Every trajectory can be dense in your surface, yet not uniformly distributed. And the most important example of this is these billiards that we talked about. In billiards with a barrier, for various values of the height alpha, there'll be a big set of directions theta that give you minimal non-uniquely ergodic directions. So this is just a warning I want to give you. There are lots of possibilities of interesting things that can happen in higher genus, and you can see them already in genus 2 with this extremely simple example. But back to Mazur. So now let's try and give a sketch of the proof of Mazur's criterion. So now what we're going to do is we're going to assume that we have two things together. We have two invariant measures for my vertical flow, and we're going to assume that we have this non-divergence property, that there is some sequence of times under which I keep coming back to a compact set where my length is bounded below. And then we're going to derive a contradiction. Okay, we're going to show that these things cannot happen simultaneously. Okay, so if I have two invariant measures, if I have at least two invariant measures, I have at least two ergodic invariant measures. Okay? The reason I say that is that the reason I'm making a fuss about that is that ergodic invariant measures have what are called generic points, points that is orbits which distribute according to those measures. A general invariant measure need not have, actually. You can build invariant measures that don't have generic points. This is very weird, but it happens. But ergodic invariant measures can be seen by orbits. Every ergodic invariant measure has to, almost every point with respect to it will equidistribute with respect to it, right? You see it. You see the measure from the orbits. They sometimes this is called physically relevant, I think. It's more in the hyperbolic setting, but we can adopt the terminology. So this means we have these two orbits which behave differently. Okay? So let's say now that we have these two orbits that are differently. Now we also have the fact that we have a limit point for our sequence of renormalized surfaces. Let's call that surface S infinity, because this lim inf is positive. We're living in a compact set. And this means, so we have a limit surface and we have these two distinct measures. So with these two distinct measures, we have to be able to detect these two distinct measures somehow, and we can detect them on a rectangle. These measures are Borel measures, so we can detect them on some reasonably nice set. Let's just say it's a rectangle. So there's some rectangle on the surface, and I genuinely mean a rectangle on the surface, which these two measures give different values to. In particular, if my points x and y are the points that lead to leaves of my vertical flow that have different behavior, I have this property. The amount of time I spend, my y leaf spends in Q, and the amount of time my x leaf spends in Q, that difference goes to something non-zero. Okay, but now what we're going to show is this limit surface means the existence of a limit surface means that this cannot happen. So I have my fixed rectangle, and here's the picture on my original surface S. I have my points x and y, and they're kind of crossing the original guy in different ways. I'm just thinking of the lines that cross them, and they spend different amounts of time. But on this limit surface, I'm going to put, I can take these points x and put them in a rectangle that contains no singularities. That's not hard to do. And this is kind of a moderate length rectangle. If you don't want to think about the limit surface, think about something close to the limit surface. And now I run, in fact, that's maybe a little bit better, because now I can run renormalization backward in finite time. And now my rectangle has become this, so now renormalization backwards means the vertical gets longer and the horizontal gets shorter. So I went from this short fat rectangle Rn to the shaded rectangle on the left side thing, which is very, very long vertically and kind of thin. But the point is, the edges of this rectangle are the leaves of x and y. And our claim is they intersect the rectangle Q, the original rectangle Q, in different ways. But they can't. They can't. Because they don't intersect there's no room for them to do this. Right? The pattern of intersection is kind of a topological thing that's not changing. And maybe they can differ by 1 over here, sort of, if you had a transverse interval and you looked at sort of how you hit it, but they can't differ by very much. So these leaves have to hit Q in the same way. It's a really simple argument. I mean, it takes no more than a couple of pages to write this down. And that's it. That's Mazur's criterion. That tells you that, you have this, because you're really just looking at intersections of two long leaves, but now they're 2 moderate leaves with some, if you want, what I didn't draw is I didn't draw Q on SN. Q on SN is this crazy, it's very long horizontally and kind of short vertically, but the intersection pattern's the same. All right. Great. So now, part of my life is in geometry of surfaces. The other part of my life is in what's called homogeneous dynamics, where I study actions of groups on homogeneous spaces. And there, often you're interested in certain kind of counting problems. And the minute you do a counting problem and you get a main term, what you're supposed to do is you're supposed to look at what comes after the main term. So we know, for instance, now, if we have a uniquely ergodic guy, that the amount of time I spend in any set for any vertical leaf is proportional to the measure of the set. So I could subtract off the measure of the set. And then I could ask, well, I know that's going to 0, the difference. How fast is it going to 0? Can I see that it's actually going to 0 at some rate? If maybe I write a computer program and see, can I see some information about this? And so now I want to tell you a really, really beautiful and remarkable story initiated by Anton Zorich. And I really recommend you read Zorich's early papers in the subject, because you can tell that Anton knew he was opening something up. And there's a sense of kind of wonder in these papers. Like, Anton's a marvelous writer. And yes, these papers have been superseded, and now we know a lot about them. But it's really remarkable reading these kind of mid-90s papers of Anton, because he's really seeing where everything is going to go. And he's doing this with, as we said at the beginning of the first talk, computer experiments in one-dimensional dynamical systems. So let's go back to that. So I'm going to toggle between flat surfaces and IET. So if we have a uniquely ergodic IET, then for any subinterval, we know that for any point x with a well-defined forward orbit, the number of times I land in the subinterval is n times the length of the subinterval plus something that's smaller. Question is, how big is this thing that's smaller? And what Anton did is, in fact, before I show you the other pictures, is Anton said, okay, let me write a computer program to do this. Let me take an interval exchange transformation. And in fact, he looked at his interval j was one of the intervals. It doesn't really matter. You could take the interval 0 to 1/2 if you wanted. And what he noticed is that it looked like the error term also grew like a power of n that was smaller than 1. And then he subtracted off that error term. And he noticed that that also seemed to grow like another smaller power of n. And then he subtracted off that power of n, and he noticed that that seemed to grow like another smaller power of n. So he was getting numbers. He was getting interesting numbers out of this. Let me tell you maybe the 2-dimensional version of the problem, the surface version. And this is a picture, like I said, shamelessly stolen from Anton's paper. So this beautiful paper of his with this lovely title, How Do the Leaves of a Closed One Form Wind Around a Surface? So we have our holomorphic one form, and the vertical foliation is the leaves of a closed one form. It's a harmonic form if you want. You start at the point x, you follow the leaf through x up till time t. Now we kind of know what it's doing when it passes through any rectangle or passes transversely across any curve. We know how it's behaving, especially if we have unique ergodicity. So think about it as closing up if you want. Maybe eventually it does come quite close to itself, so you close it up. Think of this is a curve, so you think of it as a vector in a vector space, a vector in homology. What's the behavior of this vector in homology? Right? It's almost exactly the same question as this ergodicity question. The main term of the growth is exactly given by unique ergodicity. You grow like sort of the what's called the asymptotic cycle of omega. If you don't know what the asymptotic cycle is, you can take that as its definition. You grow like the thing so that you pick off the right transverse measure. Now the question is, what do you get beyond that? So in this picture that Anton's drawn, so you have this. So this picture is happening in homology. So this is some 2G dimensional picture. So this is, you have all these axes x1 up to x2g. You have some direction of an asymptotic cycle, right? And you look and you're sort of winding around and you're getting closer and closer to that in terms of t. And then what Anton says is, well, this vector space is not just a vector space. It's a symplectic vector space. Right? Homology has a symplectic structure, intersection number, right? The intersection of two curves is a symplectic form on homology. So let's look at this symplectic complement of the asymptotic cycle. And let's project everything to there and see what's happening. Now, all you kind of know is that you're going to be, in some kind of, you're getting kind of closer to this point. You're clustering around this point, but maybe you're going to get some growth in that in that complement. What then Anton noticed is you actually end up growing along a line in that complement. And then if you throw away that line and you look at the complement of that thing, again, you start to grow along a line in that complement. And then you throw away that and so on, all the way down to G lines. So in fact, not only were you getting rates of growth, you were getting along which direction you're growing. You're getting some numbers that telling you that your vector looks like some main term plus some error term times some lower power plus some error term times some lower power. And there's a kind of a flag associated to this growth. What does that story sound like to you? You have some kind of growth on each thing, and you have some kinds of a flag of subspaces. Of the lectures we've heard here, to me, that sounds like Bertrand's lectures. Right? It sounds like Lyapunov exponents. And in fact, they are Lyapunov exponents. What are they Lyapunov exponents of? I'm going to try and tell you that in a couple of different ways today. So try and make the connection between these deviations and Lyapunov exponents. And again, all of what I'm saying, has been known now for about 20 years, but it's just an amazing, amazing story that I really want to share with you guys. Okay, so just to recap some of the things I was saying, Zorich noticed that if you subtracted off the main term and you took sort of log of the difference divided by log n, it grew like some theta 1. And then, there's this famous, I think this famous story about, I think it was Bertrand Russell, right, who was talking about sort of cosmology, and this person said, no, you've got it wrong. The Earth is sitting on the bed of some turtles. And said, but what are the turtles sitting on? And this person said, well, it's turtles all the way down. So in this case, it's turtles all the way down. You keep subtracting off the previous error term. Again, you'll get some number theta 2, and some number theta 3, and some number theta 4, until finally you actually get a bounded error. You'll finally get something that's actually not log over log n is going to 0. You actually get genuine bounded error once you add up all of the terms with power laws. So that's actually incredibly powerful. And in fact, so this is a genuine picture from computer experiments of Zorich's in a genus 3 surface, where he took these curves, so C, I think C up to C sort of 100,000, where these curves where you take this long thing and you close it up, and he projected away from the asymptotic cycle. He looked in the complement to the asymptotic cycle, and you can see that it is growing along a line here, right? Like there's some deviation from the line, but it's sort of growing along a line. You can actually see that, I think, right? I always feel a little bit dodgy, saying things like this. There's this story about some physicist giving a talk at the Institute for Advanced Study and throwing up some data and claiming some scatter point plot and claiming that the points lay along a line. And von Neumann turns to his neighbor and sort of says loudly enough for everybody to hear, well, at least it looks like they lie in a plane. But here, I think they do actually look like they lie in a line. So Okay. So I want to tell you about these numbers, right? These numbers have meaning. They have geometric meaning. They are Lyapunov exponents. And I want to tell you what they're Lyapunov exponents of. But let me recap what we've done so far. We got qualitative information, sort of unique ergodicities, kind of qualitative information about flows on translation surfaces from this Teichmüller geodesic flow, which renormalized them. Is there a similar strategy that can give us quantitative information, not just qualitative, but actual numbers associated to IETs and translation surfaces? And the answer is, of course, yes, there is. So one thing is, I think one thing I was remiss about last time is I told you how to get an IET from a surface. You look at the first return map to a transverse interval, but I didn't tell you how to build a surface out of an IET. There's many ways of building a surface out of an IET. For the same IET can show up as a return map for many different surfaces, but sort of the canonical way is what are called zippered rectangles. So you put a rectangle on top of each interval, you zip up for some distance, up to some height, and then remember your intervals, the tops of your intervals are glued to where they go under the IET, and so you zip down from some amount as well. So you're getting a polygon with parallel sides identified by translation. You're getting a translation surface. And where you sort of zip up to and zip down to are the potential places where you can have singularities. So here's a picture of this. This is a surface that I'm describing in a couple of different ways. One is just a translation surface. Then you can see it as kind of a zippered rectangle. I really like this terminology. I think it's very descriptive. Zip up, zip down. Okay. So what we're going to do is, remember, we were speeding up the flow before, the vertical flow. What I want to do is now I want to describe a discrete version of this process, and I'm going to try and explain the connection between these two processes. The discrete version of this process is I want to speed up an interval exchange transformation. I want to say, instead of looking at a long piece of an orbited IET, I want to tell you how to make it shorter for maybe some different IET, and say, understanding the shorter orbit of this different IET tells you something about the long orbit of your original IET. Yes? Sorry, Oh, no, of course it will, because, well, actually, the error term is not going to depend on how much you zip up or not. The error terms for the IET, because the IET contains all the information about the future. If the IET gives you the information about the vertical foliation, the heights and stuff of the zippered rectangle is giving you the horizontal foliation. So if I ran everything backwards, then of course the heights would matter. But I'm running in forward time, yeah. Exactly. So this is kind of, by fixing the IET, I'm fixing one endpoint of the Teichmüller geodesic. I'm fixing essentially a point in PMF. Yeah. Okay, so to speed up the IET, what we're going to do is we're going to use a construction that we've been implicitly using all this time called the first return map, right? So we use this first return map of the flow to a transverse interval to get the IET. We said, first return map is exactly what it sounds like. The first time you return, you keep track of where you go. And so here what we're going to do is we're going to cut off an interval at the end. We're going to shorten the interval. Notice that's exactly what would happen if you took your interval and you stretched out the horizontal. Now your interval is going to be kind of length bigger than 1. You could cut it off to make it length equal to 1 again and look at the first return map to that new transverse interval. But now we're just going to do this in terms of IETs. So what we're going to do is we're going to take some subinterval of the original interval by cutting off an interval at the end. We're going to cut off an interval at the end, and we're going to try and keep track of what happens to the data of the IET, the permutation pi and the length vector lambda. So what happens depends on what interval we cut off. Our procedure is to cut off the shortest interval possible at the right. Oh, there's bad software or bad use of the software. We cut off something, either the last interval or the interval that becomes the last interval under the IET, whichever is shorter. The reason we cut that off is that actually keeps, when we look at the induced map, that gives you an interval exchange of the same number of intervals. So your new lambda prime is an interval exchange map of the same number of intervals. I could go on and describe all the combinatorics, but I think a picture is better in this case. So the type 1 modification is the rightmost interval in R4 is wider than the interval R1, which is, so this is the permutation 4, 3, 2, 1. So what we do is we cut something off of length R1 and then we stack it up on top of R1. This is what we do to the surface, and then we just look at the first return map to this subinterval here. Okay. So we cut off the to be last interval and stack it on top. That's a modification of type 1. And then type 2 is the last interval is actually shorter than the to be last interval. We cut that off and we stack it, is narrower than the rectangle, and it's glued at the bottom. You glue it at the rightmost position at the bottom now. And so that changes, just changes the relative sizes a little bit. So you get a new R4 prime. The exact details of this procedure are things you can actually work out by hand. I can write down, the upshot of this is the lambdas, the length vector, changes by an elementary matrix, by a matrix with ones along the diagonal and one -1 entry. The permutation changes in a way that's a little bit more complicated. Let me just share with you. So lambda changes by a linear transformation with ones on the diagonal and one off diagonal 1. I'm lying a little bit because what I'm doing is some relabeling to make sure to put it in this form, but up to some relabeling. And the permutation can be easily computed as well. The set of permutations that you can get is called the Rauzy class of the permutation. So here is, for instance, the Rauzy class of the permutation 4, 3, 2, 1. So from 4, 3, 2, 1, if you do transformation type 1, you get 2, 4, 3, 1. Otherwise, you get 4, 1, 3, 2, and so on and so forth. This is a nice graph. But what I want you to think about, and very similar to what Francois was mentioning earlier, is if you think of this as kind of you can think of this as actually as a quiver, if you want to think of it that way. And in fact, each of these arrows has a matrix sitting on top of it, which is with this ones, and with the ones on the diagonal and a -1 with the off diagonal, which tells you how the lambdas transform. And what we're going to be interested in is, as you walk around, how the lambdas transform. Or actually, what we're really going to be interested in is how the inverses of these matrices multiply, because that'll tell you what's happening on the original surface, right? The -1 tells you how you get the new surface from the old surface. We're interested in what's happening in the old surface in terms of what's happening in the new surface. So we're going to be interested in these kind of non-negative matrices, ones along the diagonal and a +1. And so what we're going to do, actually, is we're just going to keep running our procedure, which will tell us how to run around on this graph, and we're going to multiply these matrices together with the ones, with mostly all ones on the diagonal and these one off diagonal entries, and we're going to see what are these matrix products we're going to get. Okay. So to each IET, by iteration, we get a path in the Rauzy graph and a sequence of 0, 1 matrices, A1, A2, AN, so that the original lengths are related to lengths at stage n by the product A1, A2 up to AN. And in fact, the ij entry of these matrices is kind of giving you information about number of visits from interval I to interval j. And in fact, what Zorich observed is the limiting eigenvalues of the matrix appropriately normalized, or the limiting logs of the eigenvalues for the matrix appropriately normalized, are exactly the deviation exponents for the IET. This is the key observation relating Lyapunov exponents and deviation of ergodic averages. Okay, this takes some time to process. And in fact, you can't really process it unless you actually work out a couple of examples. And I'm going to suggest an exercise in a minute, but before I get to all of that, I want to step back for a second and away from surfaces for a second and see what we have. We have some procedure that starts with this interval exchange transformation, gives us a sequence of matrices and says, take their products and look at their limiting, so these limiting eigenvalues. And I'm saying, first of all, there's a lot to unpack here, because I'm first of all saying that these appropriate normalized limiting eigenvalues exist. Right? That's something I'm saying. And I'm saying they're connected to IETs, but and I'm going to say that these things have a name. They're called Lyapunov exponents. But what I want to do is I actually want to tell you a little bit about the history of Lyapunov exponents and sort of where they come from. Bertrand gave this beautiful series of talks on sort of the geometric interpretation, but I want to tell you a little bit about the historical origins, which come from random matrix products. So here is something you can do in 10 minutes if you know a little bit of Python or even mathematics, whatever your favorite computer program is. Generate a sequence of coin flips, okay? Independent coin flips. So, and then if your coin comes up head, write down the matrix 1, 1. So maybe heads corresponds to the matrix 1, 1, 0, 1. And tails corresponds to the matrix 1, 0, 1, 1. And just multiply out these matrices. You will see Lyapunov exponents popping up. If you take log of the eigenvalue, top eigenvalue of your product, you will get a number, and of course you'll get a negative number. You'll have one positive and one negative number. And you will see you can do this over and over again, and you'll get some numbers. I urge you to do this, actually. It's a really fun exercise to do this. And not very hard. But that's where Lyapunov exponents came from. So classical probability theory, one of the first things people studied was sums of random variables. But here we're going to look at products of random variables. So for instance, take your favorite collection of matrices with determinant 1, let's say. SLMR, M could be 2. And then you have a k-sided dice, and you roll your k-sided dice. And let's say they're IID rolls. And you have some matrix norm. So Furstenberg and Keston showed that with probability 1, as n goes to infinity, 1 over n log of this matrix norm. So matrix norm could be largest entry, it could be top eigenvalue. It goes to a number. This is kind of a sort of a law of large numbers. So a law of large matrices. But this is actually this top Lyapunov exponent associated to the following simple dynamical system. You have the shift on this finite alphabet. Your cocycle is just, if you see symbol I, you have matrix AI, or what did I call it, MI. So you can think of it as, I have a vector bundle over the shift, if you like. And you have this cocycle, and then this is this top exponent of this cocycle. And of course, there's much more. There's in fact a filtration of this vector space, and there'll be lower eigenvalues and so on. But really, this is somehow the origin of the story. That if you take products of random matrices, you get this limit. So this was vastly and really beautifully generalized. This is one of the great theorems in ergodic theory. It's called the Oseliditz ergodic theorem, multiplicative ergodic theorem. I'm going to state it in kind of a very concrete fashion. You can state it in terms of cocycles as well, or vector bundles with the flat connection and so on. But let me state it just concretely in terms of a smooth map. So I have a smooth map from an n-manifold to an n-manifold that preserves some kind of volume, finite volume. Okay. And now, so what I'm looking at is my cocycle is just going to be the derivative cocycle, okay, of this map. This is the form in which I'm stating it. Then there exists a collection of numbers, lambda 1 up down to lambda k, such that for almost every point xm, there's a filtration equivariant under the action of your transformation f. So if you take the filtration at x and you look at the filtration at f of x, they're moved to each other by df. So it's a filtration going from sort of the trivial vector space all the way up to your full tangent space, so that if you have a vector in sort of the difference of the two spaces, in sort of the complement, you get, so if it's an LJ but not an LJ plus 1, and you look at the growth of the vector there, it's like lambda j. So it is, if you sort of take a vector at random, it grows like lambda 1, but if you take it in the complement of lambda 1, it grows like lambda 2, and so on and so forth all the way down. Okay. Raghunathan's book actually has a very nice proof of this. So these numbers are called Lyapunov exponents. And then actually, any matrix-valued cocycle, it doesn't have to be the derivative cocycle, it can be any matrix-valued cocycle satisfying this log integrability condition, works. Okay. And so Bertrand's situation was, we had there an underlying manifold, a flow on that manifold, or some process to tell you how to move on the manifold, Brownian motion or a flow. and we had a vector bundle over there, and so we had a cocycle that was just coming from the flat connection on the vector bundle, right? As you move by parallel transport, and you sort of get a matrix. And so that's sort of part of this. You can view that as part of this situation. So these are asymptotic growth rates. And now I'm really, I'm betraying myself as an ergodic theorist and a dynamicist, because I would feel ashamed if I didn't tell you sort of the real machinery behind all of this is this amazing and beautiful and really simple to state ergodic theorem called Kingman's subadditive ergodic theorem. This is, I think this is an ergodic theorem that ergodic theorists, of course, know very well, but I think every geometer ought to know this theorem. Most geometers know the Birkhoff ergodic theorem, but this is an ergodic theorem that's actually extremely, extremely useful. So take an ergodic measure preserving system, like we had. So you preserve a probability measure, it's ergodic, and take a sequence of L1 functions. Okay, so I am using the word random variable here because I shamelessly stole this from Steve Lally. So L1 random variables that satisfy this kind of it doesn't quite look like a cocycle, it's kind of subadditive with respect to the action of t. Gm plus n is less than or equal to gn plus gm composed with tn. Then, for almost every starting point, x, limit n goes to infinity, gn of x over n converges to this number gamma, where this gamma is this infimum of the integral of gn over n. It's really, so this is an extension of Birkhoff's ergodic theorem, because if you take any L1 function and you average it over the orbit and call that Sn of f, that satisfies condition 1. In fact, that actually satisfies, that's a cocycle, right? So there's an equality there, but notice equalities are interesting here. So the importance of Kingman's theorem lies that, subadditive sequences show up much more often than additive sequences. And if you have a matrix valued cocycle and you look at log of the matrix norm, it's exactly going to be a subadditive cocycle. This is the key thing in the Ocelowitz theorem. Okay. If you don't like ergodic theory, you can wake up now. We're going to come back to the situation we were at. So we digressed to a little bit about the ergodic theory behind Lyapunov exponents. And now we're going to try and talk about sort of these limiting eigenvalues of these matrices and being deviation exponents for interval exchange transformations. Okay. Any questions about this extremely brief 10-minute, showing you what Kingman's theorem is or anything like that? Kingman's should be in the 70s, I think. Yeah, Kingman's subadditive ergodic theorem should be in the 70s, maybe even earlier than that. Yeah. And in fact, this Steve Lally has a very nice, if you're looking for a nice proof of it, Steve Lally on his webpage has a very nice one-page proof of Kingman's subadditive ergodic theorem that I highly recommend. Okay, so let's go back to our IET situation. So what do we actually have here? We have this procedure of snipping off the end of the interval and looking at the first return map. That procedure is called Rauzy induction. And if we sort of snip off and then stretch the interval again to be length 1, sort of do the Teichmüller flow to it, we have a map from the simplex cross this finite set of permutations to the simplex cross this finite set of permutations. That is this, we call this Rauzy induction. Veech constructed an infinite invariant measure for this transformation. It was basically, the density was some rational function of the lengths. It was something like 1 over lambda 1 plus something or the other. And he showed that it was ergodic. So you can still talk about ergodic with respect to an infinite measure. It just means that invariant sets are measure 0 or their complement is measure 0. Zorich sped up the map. So Veech has a paper called Gauss measures for the space of interval exchange transformations, and then Anton has a paper called finite Gauss measures. And in his paper, what he said is, well, instead of doing one step at a time, let's say I do type 1, and then my next step is also type 1, and my next step is do type 1. Let's do all the type 1 procedures together. And then let's do all the type 2 procedures together. And so if you speed that up, he showed that this thing has a finite ergodic invariant measure, and that this cocycle, this matrix product that you get, has finite first moment, or finite log first moment. In particular, you can apply Ocellidit's theorem right away. Okay, now here's a very vague exercise, but it's actually quite concrete. Remember I said that the interval exchange of 2 intervals is a rotation. Work out what Rauzy induction is, work out what the matrices are, and work out what the invariant measures are in this case. The hint is the Ferry map and the Gauss map. So they're continued fractions, and the Euclidean algorithm are kind of showing up here. When you kind of do one step at a time, it's kind of the Euclidean algorithm or the Ferry map, and when you do all of the steps at once, it's the Gauss map. And you can actually, by hand, if the space is one-dimensional now, because you need, for a 2 IET, you only need to specify one number. And so you can actually work out everything by hand. The matrices are just 1, 1, 0, 1 and 1, 0, 1, 1 in this case. And that's why, and you know, that's why I told you to work this out, that there's a very close relationship there. Okay. All right, how does this all connect to Teichmüller flow? Right, clearly there's some connection, because I kept talking about we're going to make our interval shorter and then we're going to stretch it out. So how can we make this connection actually explicit? And I said, oh, from an IET, I build a surface. From a surface, I get an IET. Well, what's kind of cool is there's this kind of self-similarity in the whole picture. An IET is the first return map of the vertical flow on a surface to a transverse interval. Rauzy induction is the first return map of Teichmüller flow to a transverse invariant set. Slight lie there. It's the first what's called the natural extension of Rauzy induction is. But basically, the picture that happens on the surface is IET vertical flow. The picture on moduli space is Rauzy induction Teichmüller flow. So Rauzy induction, so to summarize this, is a discrete version of Teichmüller flow. Precisely, the Teichmüller flow is a suspension flow. What that means is you have a transformation of a space. What's a suspension flow? You have a space X, you have some transformation, T goes from X to X, and you have a function, R goes from X to R plus. So here is R of X, right? R is up here, so here's X. And now the suspension flow, and what I do is I identify X, R of X to T of X 0. And my suspension flow is I simply flow upwards. Okay? So it's the dual construction taking a first return map. And so the Teichmüller flow is a suspension flow over the natural extension of Rauzy induction. Vice versa, Rauzy induction is the first return map for a Teichmüller flow. As a concrete example, the geodesic flow on SL2R mod SL2Z is a suspension flow over the natural extension of this thing called the Ferry map. It's also, you can also realize it as a natural extension of the flow of the Gauss map. These correspond to the finite and infinite invariant measures. This is the Veech infinite invariant, has an infinite invariant measure, dx over x. This one has a finite invariant measure, dx over 1 plus x. I didn't say this. So the natural extension, so neither of these maps is invertible. The natural extension is, so if you have an interval map, the natural extension is a map of a square, which makes it invertible. So you sort of, you keep track of your past. You add the information about the past. So, right, because the Gauss map sort of only tells you how to go forward in the continued fraction expansion, tells you how to move forward in time, tells you the forward endpoint of your geodesic. We keep track of the backward one. Then we get the full data. So I don't want to go in more detail than that, but maybe actually an example is good. So here's a simple example. if you look at the map of multiplication by 2 mod 1, so take the map of the interval, which is multiply everything by 2 and then look at what comes after, look at the fractional part. So let's say, so 3/4 would go to a half, for instance. This is a shift of binary digits, right? So if you have the binary digits, it's a shift. The natural extension of that is what's called the Baker's transformation. It's a map of the square where you cut the square in half, you do this, and then you reassemble it. Right? So you add another piece of data. All right. So what have we done? Because there's one more story that I want to tell. I know I've gone very fast in this story, but what I hope is I've piqued your interest to go and actually look at these papers of Zorich and the subsequent work. So what have we done? We gave a translation surface version of Bozhenitsyn's criterion. We explained what Rauzy induction is. We explained what Lyapunov exponents are. And we hinted at the connection between deviations of ergodic averages and the Lyapunov exponents of this cocycle. So because these matrices were keeping track of visits from one interval to another, so their growth was related to the deviation of ergodic averages. The first exponent is kind of a 1, which gives you the actual just growth, the actual unique ergodicity. The subsequent exponents tell you the deviation, the lower order terms. Now, just because it's another part of a favorite story, I want to go to the second part of this now. I want to develop a strategy. So we've talked a lot now about sort of generic trajectories on my translation surface, trajectories that become equidistributed. And when we talked about them, we hinted at this idea of saddle connections, of trajectories that start at 1, 0 and end at another. These were kind of the exceptions, the points that we weren't considering. Well, now I want to consider them. I want to understand what those things are. And if we have some time at the very end, I'll try and connect the two stories. But we're now going to be into the second part of the goal, which is develop a strategy for understanding how to count special trajectories on translation surfaces. So we're going to discuss the counting problem. We're going to discuss this Eskin-Maser and Veech strategy that links these problems to equidistribution on and volumes of strata. And then at the very end, if we have time, we're going to state a kind of miraculous connection between counting problems and Lyapunov exponents. All right. So for this, we go back to saddle connections. So remember, a saddle connection is a geodesic connecting two zeros on a translation surface. And then the holonomy vector is the integral of omega over gamma. It's how far you went horizontally and how far you went vertically. So for example, let me just draw one example here. So let's say I had an L, which was made up of 3 squares, okay? All of these were length 1. So there's a saddle connection. Its holonomy vector is just 1 plus I, because I went 1 up if these are unit squares. Right? I went 1 up and 1 across. If I go this one, which goes halfway up and then like that, right? That's also a saddle connection. And that has holonomy vector, well, I've gone across 2 and up 1. So that has holonomy vector 2 plus I. Right? Just to indicate what holonomy vector. Actually, sorry, not 2, 4. Because I went across this thing twice. Right? I went horizontally 4 and up 1. So similarly, that one would give me, that vector gives me, I went up 2 and across 1, so that's 1 plus 2i. And I'm going to interchangeably go between complex numbers and vectors. And the key point is this set of saddle connections is equivariant under the action of SL2R, almost by definition. If I move the surface by SL2R, I move the saddle connection by SL2R. Right? And we, last time we looked at this picture, this is this very pretty picture of some saddle connections on a particular translation surface. Okay. So our goal is to count the number of saddle connections of length less than r. We have some saddle connections. We talked earlier that this is a discrete subset of the plane. So let's count it. So for the torus, how would we do this? For the torus, well, first of all, there aren't any saddle connections, right? There's no singular points. But let's put a marked point at 0, and let's say trajectories connecting that to itself are saddle connections. So then saddle connections are primitive integer vectors in the plane, right? For the square torus, certainly a closed trajectory from 0 to a trajectory from 0 to itself is an integer vector in the plane, but I don't want it to pass through itself more than once, so it has to be a primitive integer vector. That is, the coordinates have to be relatively prime. And that's well known that this count is the volume of the ball, so it's pi r squared divided by zeta of 2. So it's 6 over pi squared times pi r squared. This is, I mean, it requires a little bit of elementary number theory. You need to know how to do mode conversion, for instance, to give a proof of this. But let me give now a general strategy that actually works in the case of the torus as well. It's sort of ridiculously complicated for the case of the torus. So the strategy was developed by Veech and sort of pushed forward by Eskin and Mazur, and it was developed after Veech, and Veech told me this story himself. He was visiting Marseille, and Margulis was giving a lecture that afternoon. He had landed in Marseille. Margulis was giving a lecture on what's called the quantitative Oppenheim conjecture, about counting solutions to certain inequalities involving quadratic forms using dynamics. And Veech was like, well, I wanted to stay up. I wanted to get over my jet lag, and of course I wanted to go hear Margulis speak. So he went to Margulis' talk. Margulis wrote something down that was very interesting to Veech, and Veech was sort of so jet lagged, he said, well, I couldn't pay attention to the rest of the talk. But in that kind of jet lag state of mind, I thought, well, maybe this thing that Margulis wrote down could work in the translation surface setting. And it did. And Veech was able to sort of push this. And so the idea, which will be familiar to those of you who have thought about the space of lattices, is that take a function which is continuous or even bounded and compactly supported on R2 or on C, and define a function on the space of translation surfaces by just adding up the function at the saddle connections, at the Holden-Omi vectors of saddle connections. So in particular, the count is just this is called the Siegel-Veech transform. The count is simply the Siegel-Veech transform of the indicator function of the ball of radius r. Great, so I've simply sort of restated the problem. But there's a clever, what we're going to do again is we're going to move from trying to understand a problem about a fixed surface and looking at the fixed surface at different scales, right? You know, before we were looking at a long piece of trajectory, now we're going to look at sort of larger and larger balls. Instead, what we're going to do is we're going to move the surface around and try and look at everything at a fixed scale. We're going to renormalize again. Okay. And actually, yeah. So here's an idea, and in fact, the quadrilateral is a little bit complicated, but let me try and draw this picture for you. Let Q be, it doesn't actually have to be a quadrilateral. You can do this work with a triangle as well. But everything works for a triangle. So maybe I'll draw it for the triangle. So the idea is we're going to take a triangle with vertices at 1, 1, and 1, negative 1. Okay, this is slightly different. This one is oriented around the vertical. Mine's oriented around the horizontal, so apologies for this. And now we're going to ask, so remember, GT is my matrix e to the t over 2, 0, 0, e to the minus t over 2. And r theta is rotation by angle theta. And so now we're going to ask when, maybe I'll just make it around the vertical. Sorry, just to make this easier and more consistent. So we're going to ask, when is GT r theta v in this fixed triangle? Let me call it script t. Well, that means that r theta v has to be in g minus t of this. But g minus t of this, it stretches the vertical. So this is going to be very tall and very thin. So this will be minus e to the minus t over 2, and then e to the t over 2. This will be e to the minus t over 2, and e to the t over 2. But this is, I mean, this flat piece, it's almost an arc of a circle. If the circle is very large, right, it's almost flat. So for instance, for a vector, for r theta to v to land in here, first of all, the norm of v has to be less than e to the t over 2. And then theta has to be in this very narrow wedge of angles. The wedge of angles is roughly of size e to the minus t. Right? Because that's the slope of each of these lines is e to the minus t. Or inverse slope, whatever. I take Francois' cavalier attitude towards signs. So I did this for the trapezoid here. But the idea is you do this integral. You ask, so this, what does this integral count? This integral counts the measure of the set of angles which qt, gt, r theta, v lands in this thing. You get e to the minus t if v has the appropriate length and 0 otherwise. So if you put r squared equals e to the t, this integral gives a weight of r to the minus 2 to each vector with the appropriate length. And so the n of r, or n of r minus n over r over 2, is roughly the sum of this integral over all holonomy vectors multiplied by r squared. So let me skip that. That is, n of r minus n of r over 2 is r squared times this sum, which now we interchange the sum and the integral. Now it's, I lost a 2 pi somewhere there. There should still be a 1 over 2 pi out front. It's the integral of chi hat, where chi is just this chi q. That is, it's the integral over moduli space of a fixed function over a varying set of surfaces. So I need to count how many saddle connections are in this fixed quadrilateral or triangle as my surface varies. And notice this is kind of getting to be a bigger, this set of surfaces is a bigger and bigger sort of circle inside the moduli space of translation surfaces. So if we could show that these measures supported on these pieces of orbit kind of spread out evenly, if they sort of equidistribute according to some measure, we could solve our counting problem. For that, we first need a measure on the space, on this space of translation surfaces, or measure on strata. And remember, our stratum of translation surfaces with this, space of pairs x omega with a fixed order of 0, well, building a measure on there turns out to be very nice. What you do is you first build a set of coordinates. You put coordinates on the stratum by fixing a basis for homology rel the singularities. And then you take periods of your one form on this basis. Any basis will give you local, so these are local coordinates. So I should have said local coordinates up there. That is, we're viewing omega as an element, your one form is an element of relative cohomology. So these are coordinates modeled on a vector space. And now, in these coordinates are actually just sides of the polygon, right? When you cut your surface up along a basis for relative homology, you get a disk, right? And your vertices, potentially with vertices at the singular points of your surface, right? And so this is your polygon decomposition. Now, if you scale the sides of the polygon all by t, how much does the area scale by? If you scale a Euclidean polygon in the plane, you scale everything by t, how much does the area scale by? Say it louder, it's not a trick question. T squared, it's a quadratic form, right? Area is a quadratic form in these coordinates. So what you do is, so Lebesgue measure means something slightly funny here. So here is my coordinate space, here is my area 1 locus. What I do is I take the Lebesgue measure in coordinates of the set of surfaces of area. If I want to know the measure of this subset of the set of area 1 surfaces, I take the set of surfaces of area less than or equal to 1. And I take the Lebesgue, honest to God, Lebesgue measure of that set. By the way, this is exactly how Haar measure on SLNR. You can construct Haar measure on SLNR. It's not a quadratic form anymore, right? But it's look in Mn of R. take the determinant equals 1 locus, and then look at the determinant less than or equal to 1 locus. And that's how you get our measure on SLNR. This measure is clearly SL2 invariant, because SL2, what's SL2 doing? It's acting by determinant 1 transformations on each copy of R2. And so it's preserving the Lebesgue measure on R2 to the n, which is my coordinate space. So it's clearly SL2 invariant. What's not so obvious is that it's finite. That's a deep, deep theorem of independently of Mazur and Veech, that this measure is finite. And it's ergodic with respect to SL2. But this now allows us to use ergodic theory, right? We're going to use ergodic theory. We're going to use this ergodic theorem of Neveu's, which says morally, now do not quote this statement. This statement has a lot of lies in it, but morally this statement is true. If SL2R acts ergodically on a nice probability space, which also has some topology, for almost every x, you look at f of GTR theta x d theta, it converges to the integral of f over the whole space. So you're integrating over a bigger and bigger piece of orbit, it converges the integral in the whole space. So how do we use this? By the way, there's a funny story about this, which is this ergodic theorem of Neveu's is used in a paper of Eskin and Mazur's, which does this counting result. It never appeared in the literature anywhere else until finally a couple of years ago, a bunch of us convinced Amos that he actually should write it down so there's an actual reference to this. Because otherwise it existed only in the paper of Eskin and Mazur and without a proof. Now there's a paper on arXiv that actually has a proof of this. Yeah. Essentially, this uses ergodicity of the horocycle flow. This is essentially what's hiding there. That's a comment for the experts. But look, if we want to claim sort of quadratic asymptotics, all we need to do is understand that right-hand integral, right? We'll have r squared times that right-hand integral, but that right-hand integral is exactly an integral of the form we were just talking about in Neveu's ergodic theorem. So applying Neveu's ergodic theorem, we get for almost every omega in a stratum, we get that this integral from 0 to 2 pi, integral of chi hat q of GTR theta x is equal to integral of chi hat q. That is, it converges to sort of for a random translation, the number of points for a random translation surface in this quadrilateral or in this trapezoid. This actually works for any SL2R invariant probability measure on the stratum. And this, by the way, everything here is a strategy of Eskin and Mazur's. And this allows you to conclude now that there's this constant on the right, so that almost every omega in your stratum has quadratic growth of the number of satellite connections, and that's your quadratic growth constant, that integral. Okay, but how do you evaluate this integral? This is just some integral. Wouldn't it be nice if I could tell you this integral is a number? Right? That would be cool. No, the ergodic theorems, you can have SLN acting, and then you can average over K. And in fact, that's easier. SL2 is much more singular, the operators. So Neveu and Stein have things for SLN, and there's this beautiful book by Gorodnik and Neveu, which has ergodic theorems in great generality. The SL2 case is tricky because the sphere somehow is a very singular operator. If you think about things in sort of H2, sort of all your mass is living near this edge. So it's a little more, but it works for higher rank as well. In fact, that's what Eskin, Margulis, and Moses use in their their quantitative Oppenheim papers. They use that kind of equidistribution. And Nimish Shah has a bunch of results in this direction. Okay, so going back, I want to tell you how to evaluate this integral, and then we'll kind of stop there. So f hat of omega is the sum of f of v over v and lambda omega in this set of holonomial vectors. So Veech proved the following absolutely gorgeous formula. There is a constant. So suppose you have an SL2R invariant measure, and f is for every f in CC over R2, f hat is an L1 of the stratum. And Veech also proved this for the Mazur-Veech measure and for many other measures as well. So you prove that that condition holds. Then he said that the integral of f hat over the stratum is just a constant times the integral of f over R2. And as a corollary, we get that if you have Measures-Veech measure, then for m, almost every omega, n of omega r converges to this what's called Siegel-Veech constant for this formula. So there's a constant, and then you can actually compute this constant. I'll tell you a little bit about that in a minute. So let me skip that. But I want to give you an idea of proving maybe the easy part of proving the Siegel-Veech formula. So under this assumption that f hat is actually an L1 for a continuous compactly supported function, then the map f goes to the integral of f hat. What have I done? I took f, I summed it up over some vectors, and then I integrated it over some surfaces. So I've just been doing adding, right? Summing and integrating are just adding. So it's a linear map, right? If I took some constant times f, I'd get some constant times this number. If I added two functions, I'd add the values, right? This is to a function f on CC of R2, I'm associating a number. What do we call that? That's a functional, right? It's a linear functional. Think back to your analysis class. What's a linear functional? A linear functional is a measure. So it has to come from integration against a measure on R2, but we have a weapon up our sleeve. The weapon up our sleeve is that this measure dm is SL2R invariant, so this functional is SL2R invariant. So it has to come from integration against an SL2 invariant measure. There aren't that many of those in R2. SL2 acts on R2 with two orbits, 0 and everything else. You can actually do some computations to show that 0 doesn't show up, the delta measure at 0 doesn't show up. And then there's only one invariant measure on everything else, well, up to scaling. It's Lebesgue. And the amazing thing is, you can, so now you get this number. Once you decide on a scaling of the measure on R2, you get a number. But remember, deciding on the scaling is also the same thing. There's only one normalization to fix once and for all. Oh, so the question now is, can you actually compute this function? Can you compute this constant CH? And now actually the answer is yes in a huge number of cases. In a huge number of cases, and the constant is known to be sort of a rational number times the power of pi. This constant actually is the ratio of the volumes of these intrinsic volumes of these moduli spaces. These volumes of these moduli spaces have been computed by many people: Eskin, Measures-Zorich, Eskin-Okunkov, myself, Eskin and Zorich, there's lots of Martin Moeller, John Zeige. The computation of these volumes is now a long-running industry. And it uses a lot of combinatorics, but the upshot of this is, for a lot of surfaces, we actually understand how many saddle connections there are in a ball of radius r. Let me tell you one important set of examples where you can compute it quite easily. An important set of examples are surfaces which have a lot of symmetries. What do I mean by a lot of symmetries? This SL2 action on the space of translation surfaces is ergodic. So most points have trivial stabilizer under SL2R. Most points don't have anything except the identity under SL2R that preserves it. But we've seen examples of surfaces that have big stabilizers. The torus has SL2Z as its stabilizer. There are other surfaces called, so we call the stabilizer SLX omega. A good exercise using the discreteness of the set of saddle connection is that SLX omega is always a discrete subgroup of SL2R. And we say if SLX omega is a lattice, we say X omega is a lattice surface. So this is a surface with a huge degree of what are called affine symmetries. These are kind of affine diffeomorphisms. Smiley showed that the SL2R orbit of X omega is closed if and only if X omega is a lattice surface. And then, so what that means is if you're working with a lattice surface, your universe is just the SL2R orbit. It's SL2R mod SLX omega. It's a homogeneous space. You can forget about the rest of moduli space. And then the constant is actually just a covolume of SLX omega. In the torus case, the covolume of SL2Z and SL2R is zeta of 2. That's where the zeta of 2 factor comes in that setting. So Veech knew how to do this. Okay. So I think I'll actually stop there. So hopefully I got to some of the motivations and some of the goals and gave you some perspective on how renormalization, the SL2R action, so again, if you take nothing else out of this, actually, I'll say this last thing. The point is, the action of SL2 on the space of translation surfaces gives you interesting information about individual translation surfaces and dynamics and counting on individual translation surfaces. So I'll stop there.
Let's thank the speaker. Any questions? If not, then let's thank the speaker again.